With that, we'll move directly into REDHAWK and RF-NoC integration by Patrick Wolfram from GRCon Technology.
All right, thank you. So obviously today I'm going to be talking about REDHAWK and RF-NoC integration. I'm Patrick Wolfram with GRCon Technologies. We do a lot of work with SDR and specifically REDHAWK, but we're not going to be buried with it on our gravestones. So what am I going to talk about today? I was going to talk about what RF-NoC is. It seems like everybody has a pretty good understanding of that. So I'm only going to cover the main points that are important to what I'm showing you today. Then I'm going to talk a little bit more about what REDHAWK is, what problems it solves, what it gets you, et cetera. Then there's a couple of different integration patterns you can use for FPGAs and REDHAWK, and I'll explain both of those before demonstrating what I actually built using one of the integration patterns. And then I'll open up the floor for some questions. So we all know RF-NoC is a framework that allows you to integrate your IP in a simple way into usurp FPGAs. It's, at least for me, the important part is that you can hardware accelerate your existing signal processing applications using the FPGA's fast hardware. It accomplishes this by modularizing your processing into blocks or computation engines. It uses a standard set of interfaces, one for data flow and one for command and control. Basically, you can use registers and I believe AXI for command and control, and then AXI for your data flow. So if you have a bit file with blocks, or no, sorry. If you have an IP from a vendor or from an open source repository or something you developed in-house, whether it's in Verilog or VHDL, you can wrap it in these standard interfaces. A different developer can do the same thing in a vacuum, and then ideally, you can integrate with zero cost. Another really important part is the ability to connect your blocks together after the bit file has been loaded and in different configurations. So then, without reloading your bit file, you can get different behavior. So if you have blocks A, B, and C in a bit file, you can connect blocks A and B, push some data through, get one behavior, disconnect those blocks, connect blocks B and C, push the same data through, and get a different behavior. So compared to how a traditional application works, normally you have your FPGA, you load your bit file, we'll say it's a BPSK DMOD, and you have all these logically separated parts, your splitter, your PLL, your multiply, et cetera. Excuse me. And they're logically separated, and you can probably set properties on each one separately, but they're not actually physically separated. If you wanted to tap off the output from each one of those, you'd have to go in, edit your VHDL, resynthesize, and then relaunch your bit file. With RF-NoC, it's a little different. You have these modular blocks, these computation engines, and when you launch the bit file, they're unconnected, and you can connect them in any way you want, as long as you adhere to specific data types and vectors versus blocks. So you can connect them up just like you would normally in a traditional FPGA application, or you can, like I said, tap off your output and your input to your host so that you can debug the blocks individually. Now, I'm going to switch gears a little bit and talk about system integration. It's a hard problem. Usually for big solutions, you're going to pull technologies from multiple places. It's going to be multiple languages, multiple frameworks, et cetera. You're also, if you're going to scale, you're eventually going to need more than one processor, more than one host. And if you do that, then you obviously need to network things. This is not cheap. It's expensive. If you roll your own solution, it's going to be pretty specific to you, and the next guy probably won't be able to use it. Then, will it be survivable? Will it be reliable? Maybe. Will there be self-healing? That's going to get harder and harder the more you need from it. Then once you get it working, you have to support it. You have to have multiple versions, revisions, patches. You have to have people to apply those. You have to have operators who are using it and who are providing feedback to you. And then, now it's working on one platform. Management wants it to run on every other platform. Not cheap either. So what's the solution to all of this? It's a system framework, and REDHAWK is a system framework specifically designed to solve these problems. REDHAWK has multiple languages that it supports: C++, Python, Java, so that you can use existing libraries, modules, and packages. It supports multiple frameworks. Like we saw from Thomas yesterday, you can integrate with GNU Radio. Octave, not necessarily a framework, but a free open source alternative to MATLAB you can use for prototyping your DSP. And you can actually wrap that in a REDHAWK component and run it in your target application, essentially. It'll be slow, but it'll allow you to get a good idea of how things are going to work. It also has support for specialized computing hardware, FPGAs. Obviously, that's why I'm up here today. GPU work has also been done, not by me. And then there's support for specialized RF hardware, the USRPs, the RTLs, the matchsticks, et cetera. An important part of REDHAWK is that it's intrinsically distributed. You don't really have to do much to get that to work. You can have multiple hosts that will provide their GPP for you. You can have FPGAs spread out all over the place. You can have USRPs, RTLs, dozens, hundreds. You can have mixtures of this all across your domain. And REDHAWK also provides tooling for the development and operation of these systems. You have the REDHAWK IDE, which allows you to actually develop the components, devices, et cetera. I'll kind of get into those more. You have, and that's more of an engineer's GUI that you have, where you can interact with your live domains. There's also a Python REST Tornado server that you can use to make pretty UIs, and some AngularJS tools that we have. Now, Thomas touched on this a little bit yesterday, but there is a difference in GNU Radio and REDHAWK with devices. From what I understand, with GNU Radio, you have your hardware, and it's part of your workflow. And you basically rely on that specific hardware. With REDHAWK, we've tried to abstract that away by using this device abstraction. You put a standard set of interfaces between your application and the actual hardware, and then it's up to the developer of that REDHAWK device to do the translation between the interface and the actual hardware implementation. That way that you can have all these devices standing up on your network. The common set of interfaces can be used to interact with any one of them, and you can do basically capability requests. So a specific example of this is front-end interfaces. Instead of saying, I need a USRP UHD, you say, I want a bandwidth, I want a center frequency, I want a sample rate. And the first device on the network that can satisfy that request will be given to your application, and you can use it for the lifetime of the application. It doesn't really matter which device for most applications, but when you get to, say, DF, that's when you need to know, I need these antennas. These antennas are placed here. So not only do I want this bandwidth, center frequency, sample rate, I also want these particular antennas. And there's also support for that in REDHAWK. So a single REDHAWK device works well for GPPs, RTLs, USRPs, because for the most part, that hardware is very static. It doesn't change. FPGAs are dynamic by their very nature. So you kind of need two different devices to represent them. The first is going to represent the static portion of the FPGA, the actual chip, and status. You may also have radios on the chip with the FPGA itself. And then the second device is going to represent the dynamic loaded bit file portion of the hardware. So for the static portion of the FPGA, we have the programmable device. It is responsible for managing the lifecycle of your FPGA hardware. It lets you load and unload bit files, and it makes sure that multiple requests to load bit files are handled appropriately. It's also going to be responsible for controlling the RF hardware, whether that's RF hardware on the chip with the FPGA that's static, or whether it's RF hardware that's instantiated in the FPGA by the bit file. And the reason for aggregating that all in one place is mostly to reduce code duplication across all of your different devices. And then the final responsibility of the programmable device is to launch and administer the second type of device, which is, we call them persona devices because they represent a specific persona of the FPGA. So the persona device is responsible for serving as the interface for the specific bit file you're loading. It provides command and control of that bit file, and it provides data flow to and or from that bit file. So now we're going to kind of go back to RF-NoC and how RF-NoC would work with this persona pattern. The integrated RF-NoC flow is you load a bit file, and then the device itself is responsible for connecting the blocks in a certain sequence to obtain a certain behavior. So if we think back to that example of the PSK DMOD, the persona would load the bit file and connect all those blocks statically, and that is the behavior you're going to get from that persona until it's done. It connects its input and output ports to the input and output ports of the RF-NoC blockchain, and it takes all the properties of all the RF-NoC blocks and replicates those in the REDHAWK domain and advertises them to anybody who needs them. So a picture's worth 1,000 words. Here we have a programmable device and 2 different personas. We also have our hardware with some static RF, and the blank space to the right is the FPGA that's not loaded yet. So let's say persona 1 is a PSKD mod and persona 2 is an FSKD mod. At some point, something on your domain detects and classifies a signal as PSK. So some smart person or a tasker knows that persona 1 can do PSKD mods. It requests that persona 1 load its bit file. The processing is instantiated in the FPGA. The persona takes control of that processing for both command and control and for data flow. Then requests that the programmable device connect its front-end hardware to the instantiated processing. So that runs. It's putting out bits. Works great. Eventually, that signal goes down, and the domain says, all right, we don't need that persona anymore. Clear it out. So we're back at square one. Now, same thing happens. An FSKD mod gets detected. We instantiate the processing. We take control of the processing, perform data flow to and from. We may not necessarily need TX like we did with the other one. It's specific to this persona, which is slightly different than the first one. So the second implementation pattern is for hardware-accelerated components. These are similar to personas in that they are going to provide an interface to the bit file, except they're now going to provide an interface to a certain part of the bit file, not the entire bit file. So you can do command and control and data flow to that portion, not the entire thing. So once again, in the context of RF-NoC, the blocks themselves are going to be represented by REDHAWK components now. They'll be connected. If you have multiple hardware-accelerated components in an application connected to one another with bulk I/O, REDHAWK's transport, this is actually smart enough to connect them in the fabric so that you're not coming out of the FPGA and going back in, because that would be stupid. You include these in a REDHAWK a REDHAWK application description file, and the goal is that you shouldn't have to change your application if it's working on a GPP. You're just adding an extra implementation of your components so that they can be hardware accelerated automatically. And in this way, your block flow is described by the application developers, not the device developers. It's not static anymore. So another picture, another diagram. Persona 1 might be the same as before, but now we have Persona 3. And Persona 3 is a slightly different type of persona that aggregates RF-NoC blocks. So somebody allocates Persona 3. It instantiates your blocks in the FPGA, and it takes control of them. It's acting as sort of a broker for these blocks that are available. Now in REDHAWK, you have a waveform. You have 2 hardware-accelerated components in the application, and one of them needs the decimate block that's available in the bit file. One of them needs the FIR block that's available in the bit file. And for the duration of that application, those blocks belong to those hardware-accelerated components. All right, so that was a ton of information, I bet. So what I'm going to do is do a demo for RF-NoC. The hardware-accelerated component, component pattern is much more appropriate. So I'm going to focus on that. So I'm connected to my switch here. I have my laptop, which has REDHAWK installed, and it has my RF-NoC assets. And then I have an E310 with an RF-NoC-enabled UHD installation and REDHAWK also installed. So is that big enough for everybody? All right. Since I just changed out my interfaces from under myself, I'm going to make sure that my environment is clean. Now I'm going to start a REDHAWK device or domain manager. This is responsible for aggregating all of your devices and services on your network. I'm going to SSH over to the E310, and it's slow as everything these days. So while I'm doing that, I'm going to launch my IDE. Hopefully everything's not too stretched out. My Linux drivers are not happy with me today. All right. So over here, I'm going to go ahead and launch my RF-NoC device manager, which we will see has a couple of different devices in it. It's going to go ahead and get everything all loaded up. Yep. So we can see we're starting the device manager. It's hooking up to the domain manager I started on my laptop. It is now starting up the actual devices themselves, first the programmable device, and then the personas, which are going to get loaded as shared libraries, which is kind of an implementation detail that allows you to not have to create custom IDLs for your personas and your programmables to talk. Because if you had to do that for every different type of persona, you'd end up with tons of IDLs, and nobody really wants that. So now the node is started up. If I come into the IDE and connect to my domain manager, I can see that I have this RF-NoC device manager underneath of it. I have the programmable device and 2 persona devices. If I click on the first one, we can see that it has these properties. It advertises the available blocks that are in the bit file, an FFT and a keep 1 and n, and then it has the actual path to the bit file. So at this point, no, the FPGA is not loaded. This is all just running and waiting for allocations. If we look at the second one, we can see it has its own bit file, and it has the FIR and decimate NoC blocks inside. So let's go ahead and open up a Python terminal from ossi.utils, import REDHAWK. So this will pull in the REDHAWK runtime package. I'm going to attach to the domain. So this is kind of replicating what we just saw in the IDE. And I can do .id for d and dom.devices. This will show us, all right, in this list, I have these 3 devices. I'm going to go ahead and allocate the first one, which will actually cause it to load its bit file. And we can start doing some cool stuff. So that's going to block. If I come over here, we can see that the FPGA image is being loaded. That call returned true. And now if I come over here, the properties on the persona aren't different. But on the programmable device, I should have shown you guys what it looked like before. Oh, well. We can see that the hardware load status marks persona 1 as being active. It has its bit file, and it is currently loaded. We can also see that we have a couple of front-end tuners because they were instantiated in the hardware. So I'm going to launch a REDHAWK waveform. If you remember, the first persona has the FFT block in it. So I'm going to launch a waveform which uses that particular block. It'll take its time starting. This hardware-accelerated component is actually a fork of one of the existing components that you get when you install REDHAWK. It has, REDHAWK components have the idea of implementations where you can have multiple implementations of one component that might run on ARM, one might run on x86, this one will run in RF-NoC. So I simply added an RF-NoC implementation to this forked component, and now all it's really just doing is serving as a proxy to the actual FPGA block. If we look at the properties for this guy, the FFT size is set to 128. There's kind of a limit to how many samples you can pull to the host. I think it's based on the DMA channel size. So I'm not going to go above 256. So I'll go ahead and start my waveform. And right now, even though this has a reference to the FFT block, it's not actually doing anything. Once I plot the data coming out of the port, we should start to see a pretty low resolution FFT. So that actually created a streamer to the block and is now pulling the data over. It's kind of noisy looking. That could be because I have the wrong antenna plugged in, or it could just be, nope. Could just be because there's not much there. I'm going to go ahead and turn up the gain on the actual tuner and see if we get anything. Not much, still just a little bit of noise. That's okay. I can actually set the property, and since it's noisy, you might not have seen much of a change there, but it did change. So a problem with this particular waveform is it's really simple, but we're basically taking, I think it's 16 megasamples per second, trying to push them through this FFT and then pull them back over to the host, and it's overflowing like crazy. So we want something a little better than that. I'm going to shut down that plot, give it a second to clean itself up, and close down that application. So that block is no longer controlled by that application. I'm going to deallocate capacity because this is a demo. Normally you wouldn't have to do this, but I'm just trying to keep everything clean. So that's reloaded. Now I have a second application, this RF-NoC multi-block waveform. And what this is going to do is, there's also that keep one and end block in that FPGA. So if I use that, I can at least keep overflow from happening. I'm throwing away the data, but at least it's not overflowing trying to get to the host. And the way I've done that is I have a completely custom REDHAWK component, which is designed to be generic so that you can specify a block ID and you can specify properties that you want to set on the NoC block. And you can change that, I guess, at runtime. I'm not going to try it here because I haven't tested that yet. But so here's the block ID. I want the keep one and end block to be associated with this component. I have one property I want to set on the block, and that's the number n, how many I want to keep. So every 1 in 10 data packets I'm going to keep and pass to the same component we saw in the first waveform through the FFT. So I'll run that, plot the port data. So we can see it's already going slower. I'm still overflowing, but it's not nearly as much. I can go ahead and change the n value, let's say 30. So the plot's updating even more slowly now. It's no longer overflowing. So clearly it's no longer overflowing as much. So clearly I'm setting that property on the block properly. Another interesting point here is I can monitor this port to see how much data is actually flowing through there. Woo. And there's actually no data flowing through that connection. The connection is really just there to represent that in the FPGA, there should be a connection between these NoC blocks. So I will go ahead and close that down and show you a second. The second persona has the FIR and decimate blocks. So I will deallocate this one again and allocate the second persona, the RF-NoC default persona 2. Once again, it'll load the bit file. This returns true, so it was successful. And I can look at my list of waveforms. Now I have this filter decimate waveform. This is another example of forking an existing REDHAWK component. This is a tune filter decimate component. And this one's actually kind of special because it does those 3 functionalities. So I wanted to be able to do at least the filter and decimate part. So this hardware accelerated component is representing 2 different NoC blocks and hiding that from the user, basically. So if I go ahead and run this, and I'm going to plot the FFT of this output so that we can sort of see what's going on. We're filtering noise. We can see the roll-off here of the actual filter. And if we set the properties, so this resolution is not great. Thanks, Linux. All right, so I can change my filter bandwidth. I'm going to lower it down to 10,000 from 100,000. You can kind of see that the plot has updated itself. I'm going to go ahead and lower the output rate to 500,000 from 1 million. And we can see that, well, now it's a little wider because the signal-related metadata has adjusted itself and the plot has adjusted itself. We can also see that the decimation factor property of the component is now 2. If I lower it again to 100,000, it's gone down to 10. And the data rate's now so low that the plot's not updating as quickly. But we can see if I update the filter to be, let's say, 1,000 hertz. Eventually, this should get more narrow, or not. Well, that's demos for you. So basically, we hardware accelerated our filter decimate component. So if you already had a waveform that was running with the GPP version of that component, and then you installed this implementation of that component, you could run the application. The original application developer would never know that anything had changed. But now they've offloaded to the FPGA, and they're getting hardware acceleration. So I think that's all I have for my demo. I'm going to go ahead and restart this. Oh, of course. So moving forward, what would I like to improve about this? This is a really old version. Well, not really old version of REDHAWK, but it's REDHAWK 202. The 2.1 series, I think Thomas mentioned that there is the shared address space improvement so that you can have sort of a zero copy emulation. So I'd like to integrate that so that you can get as much done in the E310 as possible. The RF-NoC version I have, I think the last time I pulled in changes was probably February. So I'm sure there have been tons of improvements that'll make my code better. Right now, if you had, let's say, a SIGGEN REDHAWK component that's running on your GPP, and you wanted to push data to the FPGA and then transmit, that capability is not really there yet. I need to fix that. Also, if you had multiple waveforms, each one wants to have a hardware-accelerated component, that's not going to work because each component is creating its own UHD streamer. I know how to make that work. Basically, I just need to move that ability back into the persona, and then it's going to aggregate. I'm going to do connections for this component, I'm going to do connections for this component, and handing out the data properly. Really important here would be a code generator, because a lot of the code for the hardware-accelerated components is pretty boilerplate. And you really only need to have a couple of places where you say, insert your code here so that you can do the special sauce for your particular NoC block. And obviously, documentation at the bottom of the list. Pretty important for this stuff, because if I get hit by a bus, Thomas is going to have a good time trying to figure out what I was doing. So special thanks to Trevor Plumley. He helped me put together those graphics. They're much more artistic than anything I would have come up with, and hopefully they actually helped. Questions? Before I actually open up the floor for questions, I'd like to say we have RF-NoC for hardware acceleration. We have REDHAWK, which allows you to scale your systems. So with using this, we can scale our hardware acceleration up to dozens, hundreds, maybe even thousands of hardware platforms. So with that, do we have any questions?
Let's go ahead and thank our speaker. And could the next speaker go ahead and start getting set up?
So I do have one question for you.
All right.
That when you said you were pulling up the graphical piece, or the one that had the components, you called it a waveform?
Yes.
So what's in REDHAWK, what is the definition of waveform?
All right, that's a good question. A GNU radio flow graph would be analogous to a REDHAWK waveform. A GNU radio block would be analogous to a REDHAWK component. And then, like I mentioned, the devices really don't have an analog in GNU radio. Oops. All right, let me get out of the way.
Also, in the program, it says that the dinner and boat trips